Hello everyone, and this is Jim Corkins, and we are going to start the module on light. This is module 7. So please read OpenStack's, please read Coletta, chapters 23 on light, reflection and refraction, but also some other things, and also chapter 24, which is on curved mirrors and lenses, and also geometric optical objects. Also, other books that you might want to go to are OpenStack's, Survey, and Night, and I have those chapters listed out here. This homework is going to be related to the optics homework assignment in Physics 112. And this is related to Lab 13 in the lab book. In this module, what we're going to do, and specifically in these first the first three activities in this module, we're going to go through ray optics, how light can be seen as rays, and also what is the nature of light. We're going to also talk about what is reflection, what is refraction, specifically Snell's law, and there's a part of that which is total internal reflection as well, but also polarizing angles. What is polarized light? As far as dispersion, we're going to get into the scattering of light, and color. What is color? We'll also talk about that a little bit here in this chapter, but also how light is scattered and what is dispersion and how is that related to rainbows. So it's going to be fun. So as an introduction, we're going to be talking about what are electromagnetic waves and how are they related to light, which is carried by photons. So the two models of light is light can be a wave and light can be a particle, and both of those can be modeled here as ray diagrams, as light is just rays. And that's what we'll talk about in a moment. But mostly in the initial part, we're going to be talking about what is the nature of light. In order to talk about light, we need to talk about what are the sources of light. So how do you see things in the first place? Okay, so there are different types of sources of light. You've seen the source, the ray source, where it's just a single laser beam. It's a single beam of light, and that's, everybody has seen laser beams or laser pointers. Okay, we've also seen point sources of light, where you have one single source of light, which is a small light bulb or a diode, which extends out light in all directions. See how these little vectors are in all directions here. How that's different is that a laser sends out only one beam of light, where a point source of light sends out an infinite number of rays in all directions. Okay. Another model of light, another source of light is an extended source of light, kind of like a light bulb, which is basically a point source but just larger. So our sun can be seen kind of like this too, right? As if you're close to the sun or within a distance of the sun, it could be seen as an extended source of light, right? In the middle of a room. But another model, since the sun is so far away, we could actually view the light rays of the sun or stars, in general, even further, as kind of like parallel light ray sources, right? So if you've ever taken an astronomy class and they talk about the sunlight hitting the earth and they talk about the seasons, they usually model the sun rays as parallel beams of light. And they're not exactly parallel, and that's kind of why the sun is an extended source of light rather than a parallel light rays. But this is a way to simplify light rays, and this is kind of how we're going to actually model light shortly when we get into lenses and when we get into lenses, and we also get into spherical mirrors, and also optical geometric objects. Okay, but in the beginning here, I think we're going to deal more with light as just a single light ray, and that kind of simplifies things down to so we can analyze how light is reflecting and refracting through surfaces, through and off of surfaces or mediums. Okay. So how do you actually see objects? So if I see outside my front window, I see a bunch of bushes and cactus, and good Lord, there's a couple birdies having a big argument in the front of my house. Anyways, how is it that I see them? And some people I've heard have the misconception that that the actual object itself, like a cactus, would actually emit light. And that's not exactly true. That is not true at all. So what happens, in order for me to see that cactus, there needs to be a light source hitting that cactus, right? So when it's nighttime, and let's say it's pitch black, it would be hard for me to see that cactus, okay? Even at the distance 10 feet away, if there's a storm and there's no stars or anything like that, and it's really dark out, right? But if there's even a small light source, that light will emit light as an extended light source, and then it'll bounce off that cactus, and those light rays will then bounce off the cactus and then bounce into my eyes. Okay, so that's how you see objects, is you need a light source to bounce off those objects, so it then reflects into your eyes, or scattered into your eyes, right? And that's how you actually see an object, is light bounces off it and then comes into your eyes. And it can reflect, and it can also scatter when it hits that object, right? So it reflects if you've got like a really shiny surface to it, but a cactus will actually scatter light and also absorb light, and also emit light too. So there's like a lot of really cool things that happen when a light source hits an object that isn't shiny. It does a lot of different stuff. But really what would happen, it could actually be seen as more of a reflection for right now. So we're going to be dealing a lot with mirrors, and mirrors will reflect light. They don't really scatter light, not really, unless the mirror isn't very clean. Okay, but if the mirror doesn't do a very good job at reflecting light, 100% of light, then it does kind of a scattering pattern. Okay, so but when we talk about mirrors and actually lenses too, and surfaces of change of mediums from one medium to another, like air and water, or air and just a vacuum of space, and also vacuum of space and water and glass too, for that matter. We're going to be talking about surfaces where we're going to be talking about objects that are either opaque and transparent. So transparent is like glass, water, air, vacuum. Opaque is an actual object, like a piece of paper or a cactus, where it doesn't let light pass through it. Okay, so those are the two different types of objects that we're really talking about when we're talking about the scattering of light versus the reflection or refraction of light. So when we talk about light, what we have to talk about is the electromagnetic spectrum of light. And what we have here is a really good guide to the entire spectrum of light. Okay, and this is in terms of vacuum wavelengths. Okay, and when I'm talking about vacuum wavelengths, what I mean is that wavelengths actually change depending on the medium that you're in. So if you're in in the vacuum of space, these are the little wavelengths of light, across the entire spectrum, electromagnetic spectrum of all of light, right? But if you'd put this in air, these wavelengths would be different, okay? So it's actually really interesting, depending on the medium that you're in, and then the wavelengths would be actually changed. So what am I talking about when I talk about wavelengths? Well, let me go ahead and mark up this document. So I hit the comments button. It pops this out. I'm going to hit that little arrow back in, and now I'm able to draw with pencil. So all these tools pop up again. We got a text box, so we could edit in here. We could erase. So basically we can mark up this document, right, that we've done before. So wavelengths, basically light travels as waves. Okay, so I'm going to draw a little wave here. A little terrible wave, but that's a wavelength of light. So this is a little wave, like ripples in the water, right? And what is a wavelength? Well, wavelength is in terms of this thing called lambda, right? And so a wavelength is measured from peak to peak, okay? So ocean waves have some big wavelengths, okay? And I'm not talking about the height of the wave. I'm talking about the measurement from peak of one wave to the peak of another wave, right? So water waves, waves in water have a huge wavelength. They can be measured in dozens of feet, or even in 20, 30 feet difference, right? However, when it comes to light, they actually can get really, really, really small, okay? So here are the wavelengths on the top, right here. And if you notice, radio waves and radio waves can go from wavelengths in tens of meters to ones of meters. So basically, these radio waves can be as much as 10 meters long, depending on the radio waves, right? Microwaves, okay, so you have a little microwave oven. So this is radio. Why is that having a problem here? Having a problem writing. You know what? I'm just not going to write anything right there. So that's so this is the radio wave distance. Wavelength. Microwaves go from full wavelengths of in terms of meters all the way down to 10 to the negative fourth wavelengths. And just to let you know what that is, I'll write that here. That is, so to let you know what 10 to the negative fourth is, this is 0.001 meters. Wow, there's something going on here. So that distance is 0.001 meters, right? So that's a really small distance. It's a fraction of a fraction of a fraction of a meter, okay? Now infrared, a little bit bigger, which is weird because I think of, red as like a big wavelength, right? And that goes from 10 to the negative third to 10 to the negative 6. So even much smaller than this, right? The part of light that we see, which is the most interesting, is in this small range right here. Right here. This is our range of light. And that's all of visible light that we see. Our puppies and kitties see into the infrared, and the cool thing is that bees will see into the ultraviolet, right? So the thing that's really neat about insects is that their eyes can see into the ultraviolet range, which means, and what's really cool about that is colors of flowers that we see, we think are really pretty, but what a bee sees is entirely different, and it is supposed to be apparently very attractive to them, and that's the reason why they almost get enthralled by it. It's kind of neat. But doggies and kitties and animals can see into the infrared because they need to be able to hunt at night, and it's easier to see into that red range. And all sources of light let off infrared heat right now. So even if the room was dark and without any light, you still give off light, kind of like a small light bulb, but you give it off in the infrared range. So anything that can see in this infrared range would be able to see some source of light coming from you. So, which is really, really cool. And then we have X-rays, and then finally gamma rays, right? And they're in terms of 10 to the negative 13th meters, which is 0.1, I'd have to count 1, 2, 3. Okay, I'm having a hard time marking up this document. So 10 to the, so that was 0. A 0 point, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 meters. Okay, so this is the wavelength of basically in gamma rays area, which is super small. That is really small. The interesting thing, though, about this, that even though we're measuring these wavelengths in terms of vacuum wavelengths, okay, the color that we see is actually more linked to the frequencies, and frequency is a hertz, and so a frequency is a hertz, and that's this right here, and these are the frequencies, and 1 hertz is actually 1 over a second, which is like saying 1 second to the negative first power. So it's almost like a measurement of time, but it's actually more appropriately a measure of frequency, right? A period of time, right? So how many times in a second? So this is how many times does something occur in 1 second, all right? And so that is actually how we see light. So we see light as little photons, right? And so these wavelengths aren't changing when they go through different mediums. So what we're seeing, so even though we see wavelengths changing when we go from one medium to another, like vacuum to air to water and all that other stuff, but what really isn't changing is the frequency. And since this is the Planck's constant, and we'll talk about this in a second, what we're seeing is photons, light being carried as photons, which are massless particles. They have no mass, they have no charge, And all they basically do is they carry the kinetic energy of other particles, right? So if you want an electron to speed up, so an electron is just sitting in outer space minding its own business, right? You have an electron. If you want it to start speeding up, to have a velocity, a little photon has to come in from outer space, and I'm putting the charge up, a p superscript 0, has to hit it and it absorbs it to speed it up. If an electron needs to slow down, well, it has to eject photons, right? So photons carry the kinetic energies of particles, okay? And that's really important, okay? Because that is how we see things. When you are looking at a light bulb, it is emitting photons in all directions, okay? And so a photon has an energy associated with it, which is a Planck's constant times a frequency. So the frequency of light, which I don't have the frequencies listed here, I'm very sorry, which are very small in this range, when it goes from red, it will have a lower frequency than violet, right? This is high frequency, this is low frequency, right? So red is going to have a lower frequency, and it's also related to the wavelength, right? You basically count how many peaks are going past you at a moment of time, and that is frequency, okay? And that is frequency, and that is basically color, right? It's the frequency times the Planck's constant times, which is equal to the energy of the photon. So visible light, I have this better suited here. I have it better laid out here. So visible light in a vacuum has these wavelengths, right? Violet has a wavelength here, and red is going to have a larger wavelength, meaning red has a longer period, right? A longer period. If this wave is traveling to the right and you're counting peaks at this point, it's going to take you longer to count from this peak to this peak, right? But if you have a violet wave, which is a bunch of itty-bitty waves also traveling to the right at the same speed, and it goes through the same checkpoint, you're going to be counting a lot more peaks a lot more frequently, okay? So notice the order of this too. Red is the longest wavelength, orange, then yellow, then green, then blue, and there's also indigo in here. And then violet. So that's, you often will hear scientists talk about the spectrum of light, visible light, in terms of Roy, G, and B, I, V. So Roy G. Biv. So Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. So we talked about how light has two different models of light. Is a photon, which is the particle form of light, but also you have waves too. And we'll get more in, we talked a little bit about photons, is the energy of a photon, and that's how we see color. But really, you could also see light, which is wavelengths, right? So if you have a source of light, it's going to be it's going to be rippling through some type of medium, like vacuum of space, which I do consider a medium, air, water, glass, basically anything that's transparent. Light is going to be moving through, right? And not reflecting off of. Opaque objects, light reflects off of or scatters off of. So if you have a source of light like the sun or a light bulb or something like that, it's going to be emitting wavelengths of energy in all directions. And these are little photons too, by the way. So these little photons have their own little wavelengths, which we talked about, which is more frequencies. So this is kind of like looking down on a puddle of water. And so these are the ripples. These peaks can be seen as ripples, right? So it goes here, and where the peak is going to occur here. And then you have another ripple. And I'm going to try to make these evenly spaced. So this one right here is going to have that type of ripple. So where you see the little ripples coming out, the ripple, the top of the ripple, if you dropped a pebble into water and you're looking down on the water, you would see little rings coming out, right? Well, those rings are peaks, right? And in between the peaks are little troughs. So this is kind of a three-dimension ripple, right? So these are ripples going in off in all directions. Okay? And so what could be seen as that is almost like it's just a ray of light, right? They're kind of going in a straight line in all dimensions. So they're moving, so basically that is the velocity vector of the actual ripples, right? But what are those wavelengths, right? What are those waves that we're talking about here? Well, if you recall from what we've been studying before, as objects will emit, and especially charged objects will emit electromagnetic field, right? So light can be viewed, or actually electromagnetic waves can be viewed as a combination of the electric field, which goes along the y-axis here, and the magnetic field, right? So this could be like a charged object. This could be a charged object moving to the right in the vacuum of space, right? So this is a photon moving in the vacuum of space. Not a photon, a proton moving in the vacuum of space. It's moving along the x-axis in the direction of this green arrow. And that c is actually referring to the speed of light. So light has a speed associated, and the speed of light is 3.00 times 10 to the 8th meters per second. That is this. That's traveling at 3 and I'm going to try to count off. And I'm going to count, okay, so that's 3, and I got to count out 10 eighths. So that's 1, 2, 3, 4, 5, 6, 7, 8 meters. So light travels that many meters in 1 second, okay, which is amazing. It's amazing. Also note that the electric field is perpendicular to the magnetic field, right? And we kind of learned that a little bit in the magnetism module chapter. That the magnetic field, if you have the magnetic field pointing in one direction, that the electric field will be pointing in the opposite. It'll be pointing in a perpendicular direction. And we kind of done a problem where a charged particle was moving through a capacitor, and that charged particle moving through that capacitor, if it had, it'll be creating its own magnetic field, and then that'll be diverting its path. And this is how the electric field counteracts that, right? Well, all charged particles are emitting an electric field, protons and electrons, right? Well, that magnetic field is perpendicular to it, to that electric field, okay? So this is just the basic concept of an electromagnetic wave, like a radio wave or something like that, in a vacuum of space, okay? So this is essentially all of electromagnetic waves right here. So electromagnetic waves, how did I get that 3.0 times 10 to the 8th meters per second. Well, Maxwell basically calculated that as a combination of the electric field constant and also the magnetic field constant, right? And so this is now going to be called the square root of that is the actual velocity of electromagnetic waves through the vacuum of space. Okay? The really cool properties of this is that the electric fields and magnetic fields are perpendicular to the direction of propagation. So I'm going to go back to that earlier slide. So notice that the electric field is pointing in the y direction. The magnetic field is pointing in the z direction, which is kind of like in and out of the page. Well, the particle is actually traveling along the x-axis. Okay, so that's one property of an electromagnetic wave. Another property which we observed is that they are perpendicular to each other, and that when they're in outer space, when they're in the vacuum of space, the velocity is going to be 3.0 times 10 to the 8th meters per second. Now, when it hits air, that proton hits a transparent medium like air, it's going to have to slow down. And when we talked about when you have any charged particle, so you have a proton, that is going to be moving to the right with a velocity. If it has to slow down, it's got to emit a photon to slow itself down, right? And so in order to speed up, it's going to have to absorb a photon to speed up, right? So that's why photons are the kinetic energies of charged particles, right? So they're the ones that carry carry visible light, okay? But when this proton is in outer space, it's traveling at 3.0 times 10 to the 8th meters per second. But when it hits air, it's going to slow down, and when it does that, it's going to emit light, and that's what gives rise to basically the northern lights and things like that. I've also seen meteors, little meteorites hitting our atmosphere, and when they hit our atmosphere, the meteorites are slowing down, and the friction is basically giving off light, and emits actual light when it actually slows down. And I've seen it go from red to green to yellow, orange, the entire Roy G. Biv visual light spectrum. It was probably also emitting infrared and also ultraviolet rays too. So it's really neat how that happens, okay? So the electric field, also the fourth one is the electric field is can be measured as the speed of light and the magnetic field at any point in the wave. So before we get back to electromagnetic waves propagating, let's talk about photons. We were talking about photons a little bit before and what they are as a carrier of light, and they're the kinetic energy of other particles. So Newton saw light as little baseballs, or little balls that were moving really, really fast. It took no parabolic path, because so that way it was going really, really fast, and they wouldn't bend due to gravity, right? So he kind of reasoned that these little balls of light were moving at very high speeds in all directions, right? So Newton was, this would have been more like a flame, because he was in the Renaissance period. Sorry, I'm having a hard time doing two things at once, but this would have been a little flame of light, little wicker of flame. Flame of light. Yeah. So, and flames and light it's a source, and it would have been giving off light in all directions, and you kind of seen this. It's almost like that ripple pattern I was talking about, right? And they would be heading out in all directions. Well, if you throw a ball fast enough and it bounces off a wall, it should bounce off the same direction that it came in at, right? Well, this is interesting because this path that it takes from here to here, they're in straight lines, okay? But Fermat's principle of least time would basically say this: why doesn't it travel straight down? So Fermat's principle, and I'll use a different color to describe that, of least time would be describing why doesn't light travel straight down here and then into the person's eye. Well, if you look at it, this black path, if you measure that black path is going to be shorter than this path, right? So I'm going to try to draw that line right here. It's about the same size as this. And then this line from here to here is going to be from here to here down. Now that black path, I'll use the black color for that, goes from here to here, which I'm going to draw, oops, I'm going to draw over here. And so this distance right here is about that far. And then this other distance is also the same distance, right? Well, if you notice, the path for this from here to here is shorter than the red path, right? So it's not that light takes the path of least resistance, or it takes the shortest. It takes the easiest path, or the straight line path. Really, what's happening is it's taking the path of least time, and so that's why light actually travels as a function of least time versus resistance. Okay. So particles are doing this too, not only in wave form, but also in particle form. All right. Well, we had talked about the energy of a particle earlier. Okay. And how we see light is in terms of photons, right? Which are electromagnetic waves, right? But we talked about what we really are seeing is we're seeing the frequency of light. And we had talked about how h is the Planck's constant, which is a constant. It's 6.6 times 10 to the negative 34th joule seconds. Energy is a unit of a joule. We learned that from physics 121 or 111. Okay, so one photon, so an energy of a photon of light is basically in terms of joules, correct? So we also had talked about how, well, I don't know if we actually did talk about this, but wavelength, well, we did talk about the velocity is equal to wavelength times frequency, right? So if wavelength is equal, in outer space, this will be in outer space, so the speed will actually be in 3.0 times 10 to the 8th meters per second, right? And a wavelength is going to be in terms of nanometers for the wavelength of light, right? So that'll be in terms of nanometers. And I think some of them were 400 nanometers. Anyways, so this is this is light right here. So when we rewrite this particle, this model for using frequency, we could actually rewrite it this as Planck's constant times the speed of light in a vacuum over wavelength. And this is the energy of a photon. This is the energy for light in the vacuum of space. Okay? So we could actually calculate, based on wavelengths that we're seeing, wavelengths of light, how much energy is coming out of something, right? And if we could do that, then we could actually estimate how many photons are coming out of a light bulb per second, which is what we're going to do here. So you had learned power, which is intensity. Power is 100 watts, right? So a watt is a unit of power. So a light bulb can have really bright light bulbs will have as much as 100 watts, which is 100 joules per second coming out, right? So that is so the energy of a light bulb is going to be in per second is going to be 100 joules for every second, right? So the energy of a light bulb for that light bulb is going to be 100 joules per second. Joules per second, or actually 100 joules over the period of 1 second. So we're just going to say in the period of 1 second, that light bulb is emitting 100 joules of energy, right? So 100 joules. Well, the energy of a single photon is h times frequency, right? Which is going to be 6.6 times 10 to the negative 34th joule seconds times 1 times 10 to the 15th hertz, which would be the frequency of one of the photons, and I could look at what that is. 10 to the 15th. So that basically is this 10 to the 15th is the visible range of light. Is 10 to the 15th hertz. So it's 1 times 10 to the 15th hertz. So this right here is the frequency of light, of the band of visible light that we're seeing, right? So 100 watts over 6.6 times 10 to the negative 34th times 1 times 10 to the 15th, basically that is going to be 100, and that should say joules. 100 joules, okay, 100 joules over 6.6 times 10 to the negative 34 plus 15 is going to be minus 19th joules, right? So dividing this out, basically what we're kind of estimating here is that we're going to get 1.5, so this is going to be the number of photons that is coming out in that 1 second, is going to be 1.5 times 10 to the 20th photons. So that's 1.5, so that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Photons. This is the number of photons coming out every second from a 100-watt light bulb, right? That's amazing. Look at that. That is a huge number. It's 150 million trillion photons, which this sounds like a made-up number. It's not. All right. Well, we had talked about, the whole point of this is we could actually use this model of photons of light to actually estimate the energy of light, and we could actually use that to calculate the energy of light. If you use a intensity, you could use this. Cameramen often use this little tool to measure the intensity of light at certain points. So if you walked outside and measured the intensity of light, right there from the sun, at this point on the Earth, you could actually measure how many photons are hitting that detector per second, right? So if you measured it, and it would be giving you a number in watts. Well, just remember that watt is 100 joules in 1 second, right? So that'd be 100 joules, and this is the energy of this would be the energy of 1 photon. So 1 photon has this energy, right? Of visible light, rather. And then you could actually measure how many actual photons are hitting that detector in that 1 second. Really cool. So this model, using particles, you could actually measure the number of photons. Well, earlier we had talked about how light is traveling as waves, right? So here's another picture of what I drew earlier. And then you drop a stone in water, and you're looking down on the water. And so you see little ripples emanating, and those are the waves. Well, not only can light be seen as photons flying out from all directions, little baseballs, little photons in all directions, you could see that these waves are actually traveling in straight lines too. Well, since we're doing that, why not just view light as a particle or as a wave, and neither? Actually, just view it as its ray, as actually the direction of its velocity vector, right? So rays are actually the directions of the velocity of the wave or the particle, the path, basically the path that wave or that particle is taking. Now, you could say that a wave actually is doing a wave-like motion. Not really. If you take the average of that, it's actually just moving to the right. If you've ever watched waves on the ocean, they actually travel in straight lines, just in all directions, so radially, right? Well, if both photons and rays are taking straight line paths, well, why not just view them as straight lines? And at a very if you're very far away from something, right, well, those rays will tend to, even though if you're really close, they're kind of taking this path. But then if you get really far away, I'm talking millions of miles away from this, or actually not millions of miles, even just hundreds of miles, those rays would actually start to become elongated and straight lined over time, right? So you could actually view from a large distance that these rays of light can actually be straight lines. And so that's going to be a good model for us to use when we're viewing reflection and refraction. In fact, we're going to be viewing those two things as just single rays of light. But when we get into mirrors, spherical mirrors, and also lenses, we're going to be using this multiple parallel rays, which are parallax rays. Parallel rays are parallel to the direction of motion of the thing. It's called parallax. And that is parallel to the plane of motion. That's what parallax means. Okay? Well, all of light and even waves do this. Like sound waves will take that path, but along a very far distance, these wave fronts will actually be straight line paths, right? And so that is kind of what we're seeing. We're actually seeing the wave fronts hitting our eyes, which we are interpreting on a straight line. Again, this is Fermat's principle of least time happening. Well, now that we're looking at light as more of a ray of light versus a particle or wave, well, now we could actually look at things a lot more simplified, okay? So light will be traveling in a straight line. Light rays can cross, and a source of light. So an object, if light is coming in from the sun and hitting it, let me draw better. Light coming in and hitting it right here, well, that opaque object is going to emit that light and scatter it in all directions, right? And so you could actually then view this almost like a source of light, even though it's not the source of light. It's that object, that opaque object, is now scattering light in all directions, and it then, for that moment, you could kind of consider it as the source of light, right? Even though it's not. So this is now the object that you're seeing, and that's going to be emitting light in straight lines. And that's how our eyes are working. It's kind of focusing the light. Okay, so light is reflecting, it's refracting, it's scattering, it's actually absorbing through objects. So this is all the different types of ways that we could use light rays. Well, another thing that's really interesting as a consequence of that is now you have shadows too. Opaque objects are going to make shadows, right? If you have an opaque object, it's going to make a dark shadow, right? And it's going to have levels to that shadow. And I forget what they're called. They're like umbras and things like that. And so the cool thing about that is that if you bring this opaque object closer to the light source, well, that shadow is going to get larger, right? But then you're going to have a larger ring. If you bring it further away, that shadow is going to get closer. The closer you bring this opaque object to the screen that you're trying to view the shadow on, the closer the shadow will actually be the actual size of the object, right? So shadows are a consequence of light. And not only that, the cool thing, if you had like a water bottle, if you had a water bottle of light, you have a water bottle of light and you have a light source right up here like the sun, and that water bottle is actually, the edges of this is going to make little shadows, but this isn't going to be a perfect shadow coming off this, right? It's not going to be a little shadow. It's actually going to have little parts to it, and there'll be a light area. So if you have an object that is transparent, it's not going to make a perfect shadow just like this opaque object. So you have to keep that in mind, that it's going to allow some parts of that light to transfer through, and you're not going to see a shadow like a normal shadow. You're going to see a light area too. So anyways, so I hope you enjoyed light. So please do the labs and do the quizzes, do the labs and tutorials and quizzes associated with this. Thank you.